How many questions will be there in the quiz? A few long ones or many short challenging problems? Okay, maybe we can. Mhm. I have not made the question paper yet. I have some questions in mind. So let's see how it goes. Obviously, it will be a little challenging because it's take home. Okay, so let's begin. So we were looking at uh, how to construct more groups. If you already know some examples of groups, right? You can take their subgroups, you can take normal subgroups, you can take quotients. If you have group homomorphism, then you can take kernel or image or things like that, right? And you can also take product of groups. So these were the things which we talked about in the last lecture. Um, let's try to uh, you know uh, uh, understand some construction which is used often, some technique rather you would like to say. So let's understand this today. And then we will also see how to apply this in some concrete situation, a couple of examples, or examples meaning like a couple of theorems which we will try to prove. Not very difficult theorems, but you will see how to use this kind of techniques. Okay, so let's begin with recall quotient, right? So the idea of quotient, what was that? That we are given a group G, and G a group that is given to me, and H a subgroup. Uh, this data is given to me, all right. And what we do is this. So if this is my G, and then I have H, which is subgroup, so something like this. Then we form left cosets. So left cosets are going to be disjoint. They are somewhat a copy of H, a translated copy of H in some sense, and they cover whole of the G, right? So keep this picture in mind. Uh, then we form left cosets, G mod H. Uh, you can also work with right coset, so I'm not being biased about it, but you just get used to one notation. So look at AH, A is in G, right? So this is called G mod H, quotient. And then we try to make it a group, and G has a group structure. So using the group structure of G, we try to make it a group. And the group operation we defined as AH into BH equal to ABH. But it turns out that this is not always a group. It is a group only when H is a normal subgroup. So, so this multiplication here, this multiplication makes sense on G mod H uh, only when H is a normal subgroup. And when H is a normal subgroup, so what happens that, so when we have H, uh, rather let's use a different notation, not to be confused. When we have N, a normal subgroup of G, of G, the set of left cosets, which is denoted as G mod N as above, G in G, this is a group, is a group with the operation which comes from G, right? Is a group with multiplication given by G1 G1n into G2n to be, this is definition in a way, G1, G2n, right? So this is what we have learned so far. Uh, so the thing is this, so let's write down a little bit more about it and try to understand the meaning of quotient. So you see that whenever I have n a normal subgroup and I constructed G mod n, I can define a group homomorphism from G to G mod n. Okay, so let's define this pi. We call it pi. Uh, G going to Gn. I can define this map. This map makes sense. First of all, number one, pi is well defined. Whenever you define a map, you should first think about it whether it's well defined. Often, when you define things in algebra or set theoretic way, it's not generally too bad. So we get into habit of not checking whether it's well defined. But you should always uh, spare a second to see whether it's a well-defined map. What is the meaning of well-defined? That one thing cannot go to two things, right? That's the meaning of something saying well-defined. You can check it's well-defined. Number two, so now I have defined a map which is pi from a group G and another group G mod n, right? So the natural question arises that whether this map pi is a group homomorphism. And answer is yes, pi is a group homomorphism. And it's quite easy to check. Let's check that. So what do we need to check? Pi of G1, G2 equal to pi of G1 into pi of G2. But the multiplication here in G1, G2 is the multiplication of the group G. And this multiplication here is supposed to be multiplication of G mod n, right? Keep that in mind. So this is what we need to check. This is the question mark. Let's do that. It's kind of very easy here, but again, we need to practice. So pi of G1, G2. This is by definition. Definition of pi will say that this is supposed to be G1, G2, n, right? Now, multiplication operation on G mod n will tell you that this is same as G1n into G2n, which is same as pi of G1 into pi of G2, right? So it's a group homomorphism. It's quite easy to see. Uh, Whenever we have group homomorphism, we can ask whether it is injective or not. In particular, injectivity is decided by looking at kernel, right? Did we verify? Did we do this last time? I don't remember now, but we can check that. So, what is kernel of this map pi? That's the question we're asking. Anyone can tell me what is the kernel of this map?
The
Pi
members of the
is for
subgroup N.
projection. Yeah, so the kernel of pi is exactly n. So the question is that what are the elements of G which go to identity in G mod n? Identity in G mod n is the subset n, right? So obviously the elements of n will go to n. Every element of n will go to the class n. So that is the kernel and nothing else, right? So that also to verify that nothing else. So kernel of pi is n. So in general, it may not be injective, right? Until unless you take n to be the identity subgroup, it's not going to be injective in general. Uh, Question. Next thing is that what is the image? Is it subjective? Is it subjective?
It is right.
So it is subjective because any element in G mod n is of the form G1n, and obviously G1n comes from G1, right? So it is subjective always. So we have, so what we proved that pi is a surjective uh, group homomorphism, all right? And Uh, the notation pi is something to, to indicate it's some kind of projection. So this construction is used in all kind of different subjects. Uh, you might have seen, so this construction is quite common. For example, I don't know whether you've seen this in linear algebra. So in linear algebra, you have a vector space V and a subspace W of V. Then you have quotient space V mod W. All right, and you might also prove that if dimension of V is n and dimension of W is something. So let's write down. So what will be dimension of V mod W?
The difference.
So it will be dimension of V minus dimension of W, right? So you have a quotient construction in linear algebra. Uh, so in fact, in linear algebra also, this vector space V, which is vector space, it's supposed to be an abelian group first, right? So I just said V mod W is nothing but the group theoretic quotient which we had done here, right? However, it's another thing to say that V mod W also has a vector space structure. So you need to define, other thing also, the multiplication with scalars and things like that, right? So, but as I said, and as a abelian group, it is nothing but the group theoretic quotient, what we have defined here. Uh, you have this similar concept in topology, that if you have a topological space, you can pinch together certain points and get a new space, right? So I don't know whether you have any, probably you have not done anything to do with topology, but I can just give you an intuitive picture, an intuitive example that how this is used in geometry and topology. So keep in mind one of the example which we did. So I have real line, and from real line I can go to circle, right? Which was in complex plane. So you can think of the complex plane and the circle S1. How does it go? There was the exponential map. It's a group homomorphism. We saw that it's a group homomorphism, right? So the topological or geometrical idea is to think of the circle as like an infinite spiral, which is projected down to a single circle, right? So all the points which are on here uh, go to a single point here, let's say, right? So that is the idea. That is the idea behind defining quotient. So there is a concept of quotient space, and even in topology, it becomes a little bit of tricky to say that whenever you define quotient. So said theoretically you can define quotient, but uh, whether it will remain a nice topological space or not is often a little bit tricky. Like here, we said that if you take quotient with respect to any subgroup, it may not give you a group. So you need to take quotient with a normal subgroup, right? Only then you get a group. Okay, so this is for a little bit of motivation and what to look forward to. And this construction is not arbitrary, and it will come again and again in future in your different maths courses and even otherwise. Okay, so let's get back to doing something interesting. Uh, this is a tool which is going to be used quite often, and I will write it as a theorem. This is called first isomorphism theorem. This obviously means that there is a second one also, and I don't think I will write down a proof that. You can have a look at second and third isomorphism theorem in book, uh, which we will not use much. So So let's not just try to prove it for the sake of proving it, uh, until unless we have a lot of spare time. So, okay, first I have to write a statement before I take the proof. So what's the statement? So the theorem says this, that suppose I have, so let phi from G1 to G2 be a group homomorphism. Uh, then number one, uh, we can define, we have, then we have phi bar from G1 mod kernel of phi to G2 group homomorphism. Remember, why this is significant is because, so I sort of pointed out earlier that whenever I have a group G and subgroup H, suppose these are finite, then the size of G mod H is supposed to be size of G divided by size of H. So if you are non-trivial H, the size of G mod H decreases, right? That is why this kind of theorems are very important. Obviously, when you want to prove some major result, you can imagine that this will help you in proving those results using induction, right? So this can be induction steps. So that is why this is important. So the theorem says, first of all, that given any group homomorphism, I can define another group homomorphism from G1 mod kernel to G2. Uh, Not just that, the interesting thing is that this phi bar is injective. And if phi is surjective, then phi bar is also surjective. Then phi bar is also surjective. So sometimes people make a picture or diagram just to keep this in mind. So here is, let's make this diagram. So I have a group G1 and I'm given this map G1 to G2, which is phi. How do I construct phi bar, right? So this diagram actually indicates that construction, which we are going to use in the proof anyway. So you are supposed to have a map from G1 mod kernel of phi to G2. This is where phi bar will come in. What is this map here? We know one map, and that is supposed to be the projection map, right? Because kernel of phi is a normal subgroup of G1. So I have a projection map from G1 to G1 mod kernel of phi, and that's a natural map because it is defined using the operation of group G1. And this is what the picture is in some sense. And let's just, because I don't remember whether I said this earlier, so let's just write this here. What is the meaning of, like, we are trying to compute, I defined what kernel is, right? So we are trying to compute kernel every now and then. So what is the meaning of that? Why do we do that? So the thing is this, the significance of kernel is this. So suppose I am map phi from G1 to G2, then it's a group homomorphism, not just any map, group homomorphism. Then phi is injective if and only if kernel of phi is trivial, simply identity, right? It has only one element, identity. I mean, you can write identity as identity group, or you can write it as a set containing identity. Let's prove this, because this is something not very difficult, and this we will keep using again and again. So let's write a proof for this.
So
So
may We did prove this last time, that
Sorry,
phase
we
injection.
proved this.
Yes, bro.
Yes, sir. Yes, prove that.
Okay, so good, good. So I don't remember. I didn't check my notes also. So yeah, so but it's just good to revise. So I will not write the proof. So take it as a revision of that statement. So fine. So we have revised this. So let's get to the proof of the theorem. Proof of theorem. So first thing, so we say that given phi, I can define a map phi bar, right? So again, let's go back to the picture. That is the good way to remember how this map is defined. So I'm given phi here, and I'm supposed to define something from G1 mod kernel of phi to G2. This is called phi bar. And how this is defined is this. So I will use the map pi here. So I'm given phi. So given phi, how to define phi bar. All right. So that is what I am trying to explain, which is the first part essentially. And first part says that I have to prove that's a group homomorphism. So how to define phi bar? So define phi bar of, so phi bar is defined on G1 mod kernel of phi. So I have to take a coset here. So let's say coset is G into kernel of phi. So kernel of phi is a normal subgroup. So I will keep writing kernel of phi, or I can use maybe some other notation. But you know, uh, too many notations also make it confusing. So kernel of phi exactly tells you what it is. But kernel of phi is supposed to be a normal subgroup, right? So keep that in mind. So phi bar of G into kernel of phi will be defined to be simply phi of G, right? I know phi, I'm given phi, so I will take phi of G and I'll just define phi bar G dot kernel of phi to phi G. Why? Why should I define this way? It's quite natural. Um yeah. So this is what I have defined here, and I'm explaining you why it should make sense. See, what would be phi bar of, let's say, some element G and some other element, suppose N. N is in kernel, right? Suppose I have N in kernel of phi, right? Okay, let's not compute phi bar. Instead, let's try to compute what is phi of such an element. Okay. If I try to compute phi of G into N, what will happen? Since phi is a group homomorphism, this will become phi of G, phi of N, right? But N is in the kernel, so that becomes identity. So I get phi of G. So what I notice is that phi of G times N goes to the same element as phi of G for any N. And that is what motivates me to define this phi bar. So this is what motivates me to define what I defined earlier, phi bar. And what's the advantage of that? Okay, so first let's go one by one proving this. So first thing, we check that phi bar is a group homomorphism. I will again say that it's worth checking whether it's a well-defined map, but I will leave it to you to decide that. So let's prove this, that this is a group homomorphism. So what do I need to check? Phi bar of G1 kernel. Let's not use G1. Let's use G kernel of G times kernel of phi. This is one element multiplied with, let's say, H times kernel of phi, right? And I need to prove that phi bar of this two product of these two element is, so this is what I need to prove, that this is equal to phi bar of G dot kernel phi into phi bar of H dot kernel phi. Keep this in mind that these are quotient cosets of that group. These are elements in quotient group. So yeah, it doesn't look very neat to write kernel of phi. I could have used a single notation, a single alphabet. That would have been much better. But anyway, let's keep doing this. So I have to check this. So let's begin with left hand side, which is phi bar of G kernel of phi into H kernel of phi, right? Okay, we know how to multiply first of all two cosets, right? So I have to use that. That makes sense. So this is going to be phi bar of GH kernel of phi. Now, what's the definition of phi bar of some element? Phi bar of some element is going to be simply GH, because this is one coset, and no, not GH, it is phi of GH, because this is just one coset, and we know how phi bar is defined on one coset. It is simply the value of phi at the element. So this is phi of GH. But phi is a group homomorphism, so now I can use that. So I'll write here as a phi G, phi H. So this is because phi is a group homomorphism, right? And this step is obtained by uh, definition of quotient multiplication, right? And this step is basically here is simply the definition of phi bar. So sometimes it's good to keep writing what we are using. Okay, so phi g is phi h, but now by definition of phi bar, I can write it as a uh, phi g is phi bar of g kernel of phi, and phi h is supposed to be phi bar of h kernel of phi, right? And we proved that phi bar is a group homomorphism. What was second thing to prove? Let's prove the second part. The second part says that uh, phi bar is injective, right? So second part to show phi bar is injective. Okay, to prove injective, what we do, we'll prove that kernel of phi bar is trivial. So that is, we need to show kernel of phi bar is trivial. Let's check that. So what is kernel of phi bar? Kernel of phi bar is by definition those G kernel of phi such that phi bar. So this is an element of G1 mod kernel of phi, right? So these are those elements such that phi bar of G dot kernel of phi becomes identity in G2. Correct? This is the definition. Let's do this. So I need to find this kind of elements here. So let's compute separately. Suppose I have some element G kernel of phi, and phi bar of G kernel of phi becomes identity. What can we say about that? So I can write this side as definition of phi bar will say that this is phi of G, right? So this will say that phi of G is identity. So this will imply that G belongs to kernel of phi, right? But kernel of phi is the identity in this quotient, G1 mod kernel of phi. So this will say that if I take any element in kernel of phi bar, it is nothing but the only possible element is kernel of phi. So this implies that kernel of phi bar contains a singleton element kernel of phi. Don't be confused, because kernel of phi is a singleton element in G1 mod kernel of phi as a subset of G1 mod kernel of phi. So this is identity of this group. Yeah. So we proved that. So since kernel of phi bar is trivial, that means phi bar is injective. The last one, third part, is quite easy to see that phi is surjective if and only phi bar is surjective. Right? I mean, that is because, again, make that diagram G1 to G2, I have my phi, and G1 to G1 mod kernel of phi, and G2, this is where phi bar is. So if phi is surjective, the way phi bar is defined will tell that phi bar is surjective, and the same thing other way around, that the way phi bar is defined to be uh, uh, surjective, that will give phi is surjective. So that is quite easy. Okay. So this is what is called first isomorphism theorem, and it's more of a tool or a technique rather than actually something like a theorem. Let's use this and see how we can prove some results. Okay, so where do we use it? So let's ask this question. So we have uh, defined group, right? Uh, the question is this, which is kind of a natural question to ask, is can we classify all groups, right? Is there a way to tell me that there are only these groups? There are like 10 groups or 20 groups or 100 groups, and there is exactly these ones, the examples we know. Is it possible? Well, I mean, the very broad answer is in general it is not possible, but maybe certain uh, family or certain restrictions, with certain restrictions, we can answer this kind of questions, that yes, this kind of things can be done. So can we classify all groups? So one thing obviously would be that uh, finite versus infinite. This is simply the number of elements, right? But can you classify further within finite, right? So this is this, and can you classify further in infinite, right? These are the questions you can ask. Okay, so let's try to prove some simple uh, result which is of this nature, right? So here are the two theorems which I'm going to prove, and this will also demonstrate application of the results which we have proved so far. So theorem one for today. So suppose I have a group, so a finite group, let G be a finite group of finite order, sorry, prime order. I already said it's finite. Let's say it's a prime order of prime order. What can we say about such group? So the answer is that then G is isomorphic to the only possible group, which is Z mod PZ. Okay, this is a very strong theorem that you are saying that it's not just uh, a particular kind of group, but it is cyclic group and it is precisely Z mod PZ. And you are saying that there is only one possible group for a prime order. It's not true for other numbers in general, uh, uh, and things could be quite difficult and tricky. And there could be too many possible groups of a particular given order if it is not a prime. So if you know about that, uh, if you know about that, then you would appreciate this theorem. What's the question? Is P order of G also? Yes, yes. So let G be a finite group of prime order, then G is isomorphic to Z mod PZ. Uh, uh, for some prime P, in fact, the P is the order of group. Obviously, isomorphic means that the number of elements in the two groups are same. So the G will have same number of elements as Z mod PZ, and Z mod PZ has P elements, so order of G is P. Okay. Second theorem which we want to prove is this. Can we classify, I mean, with the tools and techniques we know so far, can we classify all cyclic groups, right? So the answer is yes. The theorem is this. Any cyclic group is either isomorphic to Z or Z mod nz for some n greater than n positive, let's say. Doesn't matter. Even if it is negative, you will just get a duplicate of that. Okay, so these are like kind of a classification theorem. And ideally, we'll be very happy if we had this kind of classification theorem for all groups, but there is no such thing so far. I'll tell you some story some other time about classification of finite simple groups. But right now, let's talk about proving this theorem. So proof. So first to prove this, I need a very simple lemma. Let me write down this lemma. Probably you already proved this in your exercises, but let's write down this first. So suppose I have a cyclic group, then uh, uh, any subgroup of G is also cyclic. G is also cyclic. So yeah, if G is cyclic group, meaning G is generated by one element, then if I take a subgroup H, that is also cyclic. The proof is that take the subgroup H and find the element with the smallest order, and that will be the subgroup. But I'll prove this lemma later maybe. Let's complete the proof of the theorem first using this lemma, then we'll prove this. So proof of theorem 1. So how do I prove theorem 1? So what are the theorem 1? So I have a group given. So let order of G be prime P. So I'm given G is a group of prime order. And what we do is this, that take, so we'll try to use Lagrange theorem. So take some element x in G. Suppose x is not equal to 1. Right, if G has only identity, then order of G is 1, and we know that there is only one possible such group. So let's not worry about that. So suppose, and since we are seeing P a prime, then obviously P is supposed to be greater than equal to 2. So it has certainly one element which is not identity, right? So I'll take one such element, and I will form a subgroup generated by this X. Clearly, size of H is at least 2, right? Because it has 1 and it has X certainly, and could be more element. But we know that Lagrange theorem, let's apply Lagrange theorem. Lagrange theorem implies order of H, which is a subgroup, divides order of G. But we know order of G is supposed to be P. So this will imply that order of H is either 1 or P. Can order of H be 1? We just said that order of H is greater than equal to 2. So this is not possible because we have order of H is greater than equal to 2. So this implies that order of H has to be P. But once order of H is P, this will imply that H equal to G. And hence, since H was subgroup generated by X, this will be also subgroup generated by X. Okay. But so far we have not proved that this is isomorphic to Z mod PZ. That will come from the second theorem. So, we have now we prove. Now we have G cyclic of finite order P, and theorem 2 will imply this is true. We are not prove theorem 2, but we'll prove theorem 2 soon, right after this. Now, using theorem 2, This will imply that G is isomorphic to Z mod Pj. Okay, we'll prove theorem 2, and this will not use theorem 1, certainly. So we are not going in circle in some sense. Okay, so proof of theorem 2. Sorry, theorem 1. Which one I wrote first? Let me go up and check. So theorem 2 is any cyclic group is either one. So we have to prove theorem 2 now. So this is proof of theorem 2. Okay, let's do this. So what are we given? That so we are given G is a cyclic group. Right? This is what we are given. G could be finite or infinite. We don't know. But what is the meaning of cyclic group? This means that G is generated by a single element. So let's say G is generated by a single element. And what is the meaning of generator? If you remember that, that means G has elements of the form. G has elements of the form x to the power 0, which is identity, x to the power 1, x to the power minus 1, x square, x to the power minus 2, this kind of element, right? All powers, right? These are the elements in G. So now suppose what I'm going to do is that define a map from Z to G. Let's call it phi. I'm going to define this map. So take any integer n, send it to x to the power n, right? So I have Z a group with respect to addition. Remember here the operation will be plus. And I have group G, which is generated by x. So it has elements of the form x to the power n. So what I will do is that n goes to x to the power n. Now my claim is that phi is a group homomorphism. Number one, and number two, phi is surjective. Let's prove this. Okay. So why phi is a group homomorphism? This is a simple verification. So let's verify that. So suppose I have phi of n plus m. This is what we want to compute. Phi of n plus m, by definition of phi, will be x to the power n plus m. But we know x to the power n plus 1 in cyclic group is going to be x to the power n, x to the power m. This is the definition of cyclic. And this will be same as phi of n into phi of m. So this verifies that it's a group homomorphism. Identity goes to identity. That is quite easy to see. So this is a group homomorphism. This is one verification. Why phi is surjective? Because it's a cyclic group. We can send n to any of the element in G. Every element of G is of the form x to the power n. So phi is surjective because G is cyclic. Now, what can we say about kernel of G? So now, what is kernel of this map phi? Right. So two things can happen. Either kernel of phi is trivial or it is non-trivial, meaning not just identity. Let's deal with the two cases. Suppose case one, kernel of phi is trivial. What is trivial? Trivial meaning like it's a subgroup containing only 0, right? But we know that when kernel of phi is trivial, this will imply that phi is injective. But I already proved that phi is surjective group homomorphism. This will mean that Z is isomorphic to group G. That's what we proved. Now let's look at the second case. Kernel of phi is non-trivial. This is where that lemma will be useful because kernel is a subgroup. Anyway, it is cyclic, which is abelian, so it's a normal subgroup. Claim is that kernel of phi will be of the form nz. Any subgroup of Z is of the form NZ. Uh, if I think some of the questions which I given in the assignment one should answer should tell you this, right? So kernel of phi is NZ. Now apply first isomorphism theorem. What does first isomorphism theorem tells? That Z mod kernel of phi, which is NZ, is isomorphic to the group G, right? We already have a surjective group homomorphism. So all I needed to do is find the kernel. Kernel is of form NZ, where uh, n is greater than equal to, you know, 1 or 2. You can take them matters. Correct. So this proves this result. Modulo 1 or 2 little steps which you need to verify that uh, any cyclic group is either Z mod NZ or Z. Okay, I think it's already time, so maybe I'll stop here. And if you have some questions, we can discuss that.
So didn't we just use the first theorem here right now?
Sorry.
We just used the first isomorphic theorem